This is Brenda Wingard-Haynes, and this is Biochem 208, and we are working our way through Unit 6. We are talking about enzymes and vitamins. On the last section, we looked at different categories such as dehydrogenases, kinases, isomerases, and carboxylases, and that we can tell a little bit about the action of the enzyme based on the name. It tells us something about what it's doing and what its substrate is. Now we want to talk a little bit more about the specificity of the enzymes. And the question is, what accounts for the shape of the enzyme? Well, remember, it's the R groups that contribute to the primary, secondary, tertiary, and quaternary structure that for most proteins gives us something that's globular in nature. Now, they may look just really globbed up to us, but for example, this might be now the binding site for our substrate. And so we will need something with that specific shape to bind there. All right, in your notes for expediency, I went ahead and drew in some shapes. Now, remember, they don't pay me to draw. However, if you want to pause the video and draw the shapes and then come back and listen to what I have to say about it, you may certainly do that. There is what we call a lock and key model, where your enzyme has a very specific shape, your substrate has a very specific shape. They come together, they form an enzyme substrate complex, and the reaction goes forward. Induced fit is something that's more moldable. You might have this original substrate binding site, but the enzyme is flexible enough to induce the fit. In that case, if it can kind of mold around the substrate, the reaction still goes forward. Then there is the allosteric, which is typically two binding sites. The first one scenario is the enzyme and the substrate can bind to make a complex, and in doing so creates a conformational change that allows a secondary binding site. Once that binds, the reaction could go forward. Or it can go the opposite direction, where one binding site will actually close the door on the other. One is known as a positive feedback loop or a negative feedback loop. Most are what we call negative feedback loops. You create a product and it will come back and it will occupy the site, which then closes the door on the secondary site. Now the question is, what happens if the shape is not correct? If you have an enzyme and a substrate and it just doesn't fit? Well, one scenario is you can get an accumulation of substrate. And sometimes this can be problematic. For example, if you're lactose intolerant and you cannot process your lactose continues to accumulate, and the way it feels to you is uncomfortable. That's what we call something that's just kind of annoying. But it can also be deadly. An example of that is Tay-Sachs disease, where a fatty acid derivative accumulates. And actually, people with Tay-Sachs tend to not live very long. They typically die as children. So that's a very sad situation. So the accumulation of substrate can be problematic, and it can range from just something that's annoying to something that's deadly. Other times you can get your enzyme accumulating, and sometimes that can be problematic, such as upregulation in alcoholism. Okay, my dogs are barking again. Somebody's coming down the sidewalk, I guess, so I'm just going to ignore them and I'm going to continue on. What we want to know is what is going to affect the activity of enzymes and why would it matter? Well, This is the whole idea. If you can't get your enzyme and your substrate to come together and have your reactions go forward, you end up with enormous problems with the accumulation of substrate and or upregulation or even downregulation of your enzymes. So, our first graph that we're going to look at is how temperature affects reaction rate. Now you can see the optimum temperature here is about 37 degrees Celsius, which is 98.6 degrees Fahrenheit, which is optimum human body temperature. Now you can see that there is a precipitous fall off, and that at around 51 degrees that this enzyme is fully denatured. So if we figure out the temperature here, and let's do it for 50 degrees plus 32, we're going to see that this is 122 degrees Fahrenheit is when you would have complete denaturation of your proteins. And so you start feeling really sick around 100, 101, 102. That is your clue that your body is trying to keep itself stabilized. Our second graph has to do with pH, and notice that the pH graph is an even more precipitous fall off than temperature. Maximum enzyme activity is around physiological pH, let's say 7.4 blood pH for simplicity. And notice what a very, very narrow range you have here. It's about 6 to about 8-ish. And anything very far from physiological pH and you have a very, very destabilized protein. Remember that acid is a very powerful denaturant, okay? And this is why we need buffers for pH constancy. All right, the last two graphs have to do with enzyme concentration, and as long as there is enough substrate, okay, so as long as you can make enough substrate, this reaction will just keep going. Your enzyme will continue to upregulate, your reaction will continue to move forward, and there is no end in sight. This may or may not be something that you would like to have. Again, upregulation of alcohol receptors is an example of this. On the other hand, do note on this curve that substrate concentration does have a maximum activity if all the enzyme has been combined with substrate. So there is a reactant dependent maximum on some of these reactions based on the amount of enzyme and substrate that you have. What begins to happen, for example, if someone has a very high fever? Well, you have proteins that begin to destabilize, which could, in theory, lead to full denaturation. Okay, remember that doesn't occur until about 122 degrees Fahrenheit, which of course death basically occurs around 106 to 107-ish. What happens if your blood becomes too acidic or you have blood acidosis? Well, remember that our enzymes and our proteins are very, very, very sensitive to pH. And therefore, we can get headache, sleepiness, confusion, seizure, diarrhea, vomiting, heart problems, and respiratory problems. And we will come back for another segment.